Question 16 wants, first of all, an equation for the complete combustion of propane, specifying using displayed formulae. Okay, so propane is 3 carbon alkane, so there's the displayed formula. And then that's going to react with some oxygens, which we'll draw in a minute when we see how many we need. And you can see that we're going to need, sorry, missed out a hydrogen there. And you can see that we're going to need 3 carbon dioxides, because we've got 3 carbons to get rid of. And you can see that we've got 8 hydrogens, so that's 4 lots of 2, so 4 waters. And I suppose I'm going a bit over the top drawing them all out, but it is kind of the safest thing to do if you really can be bothered. So obviously we've got to do the normal thing and now add up how many oxygens we need. So we've got 6 there, plus 4 there makes 10 oxygen atoms, so that's 5 O2s. So I'll just draw them in as well. Okay, so that's our equation. And then it tells us in the question that delta H for that reaction is minus 2045 kilojoules per mole. Okay, so that reaction is minus 2045. And we've got some of the bond enthalpies, but not the CH one, which we're obviously going to need here. So it's one of those where we're going to have to introduce an X to represent the missing data point and then build it in, solve it from our calculation. Okay, so we follow the standard method and we say, right, let's get the total bond enthalpies. And we do that on the left and then on the right. So on the left we have 1, 2 C single bond Cs. Okay, so that's 3, 4, 5 times 2. And we have 1, 2, 3, 4, 5, 6, 7, 8 CHs. And that's the one we don't know, so let's call that 8X. Okay, 8 lots of X, and X is equal to the CH bond enthalpy. Okay, so that's the definition of X that we're going to be using, and as we've said before, when we're doing similar things with Hess's law calculations, it's a good idea to write down that that's your definition of X. So that's all the bonds in the propane, but of course we've got the oxygens as well, so we've got 1, 2, 3, 4, 5 O double bond O's, so that's 495 times 5. So if we add that lot up, we get 3165 plus 8x kilojoules per mole. Okay, that's for all the bonds on the left hand side, the ones that are going to be broken. On the right hand side we have 1, 2, 3, 4, 5, 6 C double bond O's. So that's 799 times 6. And we have 1, 2, 3, 4, 5, 6, 7, 8 OHs, which is 465 times 8. Again, just double check that's all the bonds accounted for, which it is. And if we add that lot up, we get 8,514. So now we can make our enthalpy statement, which is that the bonds on the left are broken, so that's a positive number. So plus 3165 plus 8x. And then the bonds on the right are the ones being formed, so that's exothermic, so that's a negative number. So minus 8514 is equal to delta H, but we know what that is minus 2045. So rearranging that, we get that 8x is equal to minus 2045 minus 3165 plus 8514, which, if you work it out, comes to 3304, and therefore x is just that divided by 8, which is plus 413 kilojoules per mole. Okay, so that's your answer, that the CH bond enthalpy equals plus 413 kilojoules per mole. So you can see that's a bit more involved than some of the earlier examples, both because there were more bonds to take account of, but also because we had to introduce X to make it work. But once you get used to the principles, particularly making sure that you remember these bonds are broken, so it's positive, these bonds are formed, so it's negative, then it's actually relatively straightforward. Part C is just one of those sort of random things that you sometimes have to do, which is to take your enthalpy change of combustion, which as normally is given in kilojoules per mole, and asked to turn it into kilojoules per gram. So to do that, you work out that the MR is equal to, so it's C3H8, so 3 12s are 36, plus 8 is 44.0, which means that the molar mass, in other words 1 mole, has a mass equal to 44.0 grams. So what that means is that it's minus 2045 kilojoules per 44.0 grams. So if we divide by 44, we get minus 2045 over 44.0 kilojoules per gram, which if we crunch the numbers is minus 46.5 kilojoules per gram is the answer. In question 17, we're looking at the reaction of propane with chlorine to produce 1 chloropropane plus HCl. So if we just wrote the equation in the normal way, that would be, well, let's draw it out with a skeletal formula. Propane plus Cl2 goes to 1 chloropropane plus HCl, so that would be the balanced equation for the reaction. But it asks for us, or rather it doesn't ask us, but we know, because it's a bond enthalpy question, that it would be very sensible to write this out in terms of displayed formulae. So here's propane plus chlorine goes to 1 chloropropane, which just has 1 chlorine in place of one of the hydrogens. So it doesn't matter which one we choose, but we'll put it there, plus HCl. So that's our equation in terms of displayed formulae. Okay, so in this question it tells us that delta H for this reaction is minus 122 kilojoules per mole. So that's the overall delta H for that reaction. And it gives us most of the bond enthalpies, but it doesn't give us the HCl one, so that's what we've got to find. So again, follow the usual method, so we get the total bond enthalpies on left and right. Okay, so on the left we have 2 C single bond Cs, which is 347 times 2. We have 1, 2, 3, 4, 5, 6, 7, 8 CHs, which is 413 times 8. And we have a ClCl, which is 243. So if we add that lot up, we get 4241 kilojoules per mole. Now on this side we have again 2 cc's, so this is the right now. So we have 2 cc's, so that's 347 times 2. We have this time just 7 ch's. There they are, all 7 of those taken account of. So 7 ch's is 413 times 7. And we have a ccl, which is 346 kilojoules per mole. And we have the HCl, and that's the one we're trying to find. So again, we're going to define that. So we're going to say that X is equal to the bond enthalpy for HCl. Okay, so that's the one that we don't know that we've got to find. So that's going to have to be added to this list. And if we add that lot up, we get 3931 plus X on that side, kilojoules per mole. So we can then combine those together to make our enthalpy statement, which is that minus 122, which is the delta H, is equal to plus this side, because we're breaking these bonds, so it's endothermic, so it's plus 4241. And then it's minus this side, because we're forming these bonds, so it's exothermic, negative enthalpy changes. So minus 3931 minus X. Okay, be careful about the sign, then we're subtracting all of that, so it's minus 3931 minus X. So if we rearrange that, we get that X is equal to plus 4241 minus 3931 plus 122, which works out to be plus 432 kilojoules per mole. Okay, so that's our answer. The bond enthalpy for HCl is plus 432 kilojoules per mole.